Hello, everybody. Welcome to the March 5th, 2026 1W-MINDS seminar featuring the famous Anastasis from McMaster University. Last name Kratsios.
Yeah, good enough.
Excellent. Who was going to tell us about using neural networks to compute anything you ever wanted to. And I will turn things over to you.
Well, thanks a lot. Actually, it's pretty accurate. I have one disclaimer for two people in the audience, I think, based on what I saw. So two people might have seen the first bit, and the rest, I think no one has. So exactly. So this broadly speaking, this I think is probably, I guess, rapidly become, at least to my surprise, I think my main research interest in the last while and for the foreseeable future, or at least for a big part of it. So neural networks as circuits. Right. So on a high level, I guess this all started from I guess the main question I've been thinking about for almost like a decade, which is kind of surprising. Yeah, it's like, well, what can neural networks represent? So in the classical sense, like one would think about representation as like approximating any like reasonable function. And so the fact that neural networks can do that, if you put in the right word for reasonable, is kind of known in some sense or another since the late 80s. So literally since before I was born. Um, but here now, if we like modernize it a bit, this is sometimes framed as relevant to artificial intelligence, but it's not so clear what the relevance is to literally AI. This is maybe more of a machine learning or deep learning property that neural networks can represent like approximate functions. Like what is this to do with AI reasoning specifically? And I want to use this word reasoning and kind of put some baggage onto that word as the talk goes on. Okay, so just to give it like an example, the same example I used, I think last time I gave this talk, the first part of the talk, which is the first 20 minutes. Um, so for example, if you ask any like standard language model some basic like modus ponens kind of question, it'll if the model is reasonable, like for example GPT is or whatever, you'll get a reasonable answer, and it even will say like it's using this like basic deduction modus ponens thing, right? So what does it have to do with like the ability for a neural network to like minimax optimally approximate, say, a Lipschitz function using a certain number of parameters? To given precision, say uniformly in a high dimensional cube. Like that's what the classical approximation theorem is telling you. And it's not so clear that these things are related. And maybe they're not even related from this perspective, right? Yeah. So here's like the transition now, I guess, and like kind of like me and my group and some of my friends like thought process transition over the last few while. So going from deep learning to AI reasoning. Okay, so the first part of the talk is based on a joint paper with Dennis Zygielski, who's a PhD student of mine, jointly with a good friend, colleague, and mentor, Brad Hart, who is a model theorist, both at McMaster University. So from the classical approximation perspective, how are functions treated, right? So you say functions in RD. So those are just treated, actually the functions themselves, or the class of functions one typically tries to approximate in, they're actually treated kind of as black boxes themselves. Forget about the model, but the functions are black boxes, I'm saying. So what I mean by that is like typically one thinks of a function as just taking inputs to outputs, and at best knows some regularity about the function, like it's omega uniformly continuous, or it's best of, or something pretty much along those lines. And okay, so in that perspective, like I'm just going to use some words which will freely use for the rest of the talk. So an input or a prompt is just like some vector in RD. The output or response is just something in R, for example, and that's about all we know, right? Okay, so the best way you can do is to expect to approximate this function, say uniformly well or something, given this modulus of continuity or best of regularity or something. And really by approximation, you want to match inputs to output pairs. And that's all you know. That's pretty much all you can do. Okay, so it's kind of, you can say black box access to that function is very vague. So do we actually know more? And typically, actually, we even think about like the actual definition in some sense of a function, in some sense, a function expressible in a language, rather. What is that? It's something that could be like literally expressed or computed. So typically, we know some more about a function. It's something that could be expressed as a sequence of elementary computations. So if you look inside the black box, a function is not just input-output pairs, but it is actually something, if it's computable, it's something that's like algorithmically expressible. So let's put like a bit like, let's look inside the black box, okay? So we're gonna upgrade our approximation theory lens for the first phase of this like presentation with like a circuit complexity lens. So it's sort of some information about the algorithm computing the function. Okay, so the ideas are going to be the following. So inputs or prompts are going to be the inputs, outputs are the responses of the function we're querying. And the key point that we're adding in is the internal reasoning, the step-by-step algorithmic breakdown of this function. And here I'm thinking non-recursively, so a circuit. That's what it's going to be for me. And I'll explain who that is in more detail as we progress. Sorry. Okay. So for example, here's a nice example, I think, or a simple example, I don't know. So here's a function that takes three inputs and gives you an output. For example, maybe an algorithm computing it could be something silly, like if x1, x2 are Boolean, maybe you perform an AND. Then maybe you do some kind of quantifier elimination, so it could be even more complicated logical operation. And then maybe x3 is real valued, and you multiply these together, and you get an output, right? So this is very different than the kind of structure one would think about in classical approximation theory of function, and of course it's compatible with it, but it's more information. Okay, so what is a circuit? So sorry, a circuit is exactly kind of this. Let's formulate it a bit more. So circuit is going to be a pair of two things. So a directed acyclic graph. So that's basically the thing's going to tell you how to route inputs to outputs and where to apply computations, together with a sequence of elementary operations that are performed almost every single node in the graph, and those are called gates. So before we go any further, I want to just say one comment. So when you talk about a circuit, when we talk about a circuit, and this will change in the second part of the presentation, we fix which language we're talking about. And fixing a language here, I mean, we fix the gates. So circuits are like what's computable is relative to the language or relative to the allowable basic computations, okay? So we'll say what the gates are, and that'll determine the power of our language in some way. Okay, so our inputs are going to be, so the input nodes are just like the first nodes on our directed acyclic graph, which have no parents. So there's nothing feeding into them. Those are just labeled as variables, x1, x2, xn. And every other node, like the children, and the children of children and so on, those are like we call computation nodes. And at those nodes, we're going to attach a gate, so an elementary function that's allowable according to our dictionary, that's compatible with the graph structure. I'll hand wave that. And finally, the output, like when you get the last child there and its output, that's going to be the outputs of basically the function that the circuit is computing. Okay, so that's the response, if you will, in the previous language. Okay, so maybe the internal chain of thought, I'll add that word internal, which I didn't write here, is basically going to be the following thing. It's going to be not only the input-output relation, but also the sequence of elementary operations and the order and by which they're strung together to actually compute that function. So that's what we're going to think of as the internal chain of thought of the circuit. Okay, and the objective we're going to have is kind of to replicate this. Can neural networks actually not only do input-output pair matching or approximate matching, but can they actually correctly replicate the intermediate steps and sort of reason through that function, compute that function. So here's like now maybe the first baggage I want to put onto this word. So for now, at least for this talk, and I guess for the next tiny bit of the research program, I'm thinking of reasoning as computation, as emulation of a circuit. So something describable in this kind of algorithm, and maybe in the future it'll be something a bit more complicated. Okay, so what do we get from this new perspective? Well, here's an informal description of the main theorem of the first paper that I just vaguely mentioned. The following. So if you have any function that goes from a d-dimensional cube to Rd, little d big D, and it's computable. So this is like a machine precision kind of statement. It's computable on a computer that has p how to say p levels of precision. Okay, I wrote this over here. What's meant. And I'm going to actually ask one more comment. This is going to be reflective of actual hardware, which I think is kind of interesting. So usually a computer, usually most digital machines, when they compute to p precision, they actually have a special, at least one or two more bits allotted to them for their computation. So the point is that if you have a number represented, say, to 3 bits, you might have 4 bits to compute. And the reasons for that is that you don't want to add 2 numbers or multiply them and have overflow and have a bunch of rounding errors. Okay, so when I'm going through this theorem, I'm going to say that I'm going to look at inputs at p levels of precision like this, and my weights and biases of our model, all the parameters will have 1 extra bit of precision, and that's compatible with what's done on classical computers. And that's important, or else I would have rounding errors all over the place. Okay, so then if this thing is computable by some G circuit, I'll tell you who my language G is in a moment, but it's rather broad. I have G gates. So that's the number of basic computations I've done. And those gates are arranged in subdirected acyclic graph curly G. So this is the structure of the algorithm, like the graph structure. And this is like the number of basic computations. Then I can guarantee you that there is a feed-forward neural network, f hat, with a ReLU activation function. So very basic primitive activation function, nothing really fancy. That's the number of its neurons is roughly proportional to the number of gates, okay, required to compute the function. So in other words, if you need to do G operations, the time complexity is at most G. And here I'm saying the space complexity of my network, the number of parameters more or less, is also of the same order. That's where they're nice. And the second comment, which I'll shed some light on, it's easier to explain with the picture, is that the structure of my neural network is going to be similar to the computational graph of the initial model. Okay, so in other words, not only is the time complexity being mapped to space complexity, but actually the structure is going to be replicated. Okay, and yeah, sorry, I don't know if I'm not sure if I said that. I might have short-term memory. The most key point is that f hat computes f on our grid. So for every input every discrete, anything that's describable in this machine precision over here, for any such input that's valid, like belongs to the set, f hat of x exactly equals to the function that the circuit is exactly equal to f of x, the function computable by a circuit. So it's not approximate, they're exact. Cool. So how does it work? I think to explain how it works, it actually also kind of sheds light, I think, on this second point, this similar graph structure, as well as the first. So the idea is the following. So it's this technique which we call surgery. You first start with your function, and either you know an algorithm for it and you want to unroll this onto your network or emulate it, or you use some abstract circuit complexity theory result to say that there exists an algorithm which is no worse than this big. So that's how you use this theorem. Okay, so once you have that, you say, so either you know it or you know its bounds on its size by some existence theorem. So there's some circuit computing app. What you do is now you do the following surgery operation, which every time you have a node, you remove the node and you look at which gate is attached to it. For example, if this is an AND, you pop it out and okay, you look up this massive table. So the proof is rather long and tedious, but it's super constructive. So in our table, we'll have like a very long list of completely explicit neural networks which do a bunch of basic computations. So for example, if this was an AND, you remove the node and you replace it by a small network computing AND exactly, right? And we have expressions for everything here. For example, if this is a NOT, I don't know why this network is so big, but you pop out this node and you remove the gate and you replace it by a set of nodes, like this little neural network that computes the NOT exactly for the relevant inputs. And for example, this is multiplication in the previous example. You remove that and modular multiplication, I guess, and you remove this and you replace it by a little network that does exactly modular multiplication. And again, in our paper, there's exactly explicit expressions for all of these. So it's not just existence, it's completely constructive. You can implement this as an algorithm at some point. So that's what I mean. And you notice that here, so the computation by construction is exactly the same because this operation is exactly this operation, this one is exactly this guy, and so on. So if you collapse these small networks, you'd recover these previous things. But second of all, what I meant by having similar graph structure is exactly that, yeah, collapsing these nodes will recover the initial graph structure, or expanding these out gets you this one. So there's two-way relation. And just to give it like a speed run through, like which gates we can handle on the finite precision world in that paper. It's pretty much most logical gates one would consider in some sense. So you can do zeroth order logic or predicate logic. And the key point is the complexity of any of these operations is linear in the number of bits. Cool. You could, just as a proof of concept, do higher order logic, but of course it's going to scale badly. But surprisingly, you could do something like quantifier elimination. And this, I want to emphasize, is critically important that we're doing, that we have this finite machine precision, because quantifier elimination is like a mixed supremum operation. So of course it's going to scale up exponentially, but it's doable. But let's just say like the proof of the second, like the point I'm putting this down here, just to say that you could do higher order logic, but most people are probably doing first order logic, which scales well. You can do basic arithmetic. Here, all my arithmetic is going to be modulo 2 to the p, whatever. So because that's the precision you have, so it has to be compatible with that structure. So you can do basic modular arithmetic. You can implement bump functions. Again, everything here besides the higher order logic is scaling linearly in the number of inputs, basically, or dimensions. You can do tropical operations like max, median, majority votes. And recently we learned some other ones with Mark too. So you can do other stuff too, which I won't say. And then you can do some formal bit manipulation operations, which I'll just skim through quickly. Basically, you can exactly encode maps that take finite precision representations of a real number, that's a finite precision real number on a little grid, and map them to a Boolean cube and vice versa, and play with that Boolean cube. So basically, pretty much every operation you could ever imagine requiring are exactly computable and completely explicit. So what are the consequences? So again, the key consequence is that neural networks scale with the complexity of the reasoning task. So unlike minimax approximation results that say like most things are impossibly hard, you need exponentially large networks. Here we're saying that if you know your task is computable by some algorithm that's small, then the network is going to be small too. Even if you want to use this only as an existence theorem, not constructive. And if you wanted to actually use this as an algorithm, like a meta algorithm, you can technically use our proof to actually take any algorithm you want and unroll it into a network and emulate it exactly. Okay, so again, so high level, time complexity becomes space complexity in the network, and the automatic, just to make this like, just emphasize this point a bit. So if you knew some algorithm was logarithm is easy, so it's can be done in log time, then this theorem, this meta, like our theorem, automatically guarantees that a small network, a log space network, can make the computation. If it's poly time, then you don't need more than poly number of neurons. And now we come into we're slowly progressing to the realm of like old school approximation theory, where like if an algorithm is NP hard, okay, then you'll need exponentially many, or like at least super polynomially many parameters to do that. So just to give an example of something that's not like a classical approximation theorem before I relate it back, is it for some reason, if you're interested, I mean, I can imagine many reasons why, you wanted to create a neural network that exactly, or you want to ask yourself how big is a neural network needs to be if you need to solve the all shortest paths problem on a weighted graph with n vertices. The inputs of the function here are the positive edge weights, and the outputs are the pairs of distances. Edge weights have to be, of course, finite precision. Then you need to at most cubically many neurons, which is not something that's in any way obvious from a classical approximation theorem. Another thing, just to relate it to other modes of computation, is if you have like a fixed budget of time, t, which you don't want to do more computation than like iterations there. And if you take a Turing machine and you run it and you record all the states up to time t, and you stop it no matter what at time t, then I can give you, by basically first mapping this to Boolean problem and then emulating the Boolean problem, I can come up with a neural network that requires no more than roughly quadratically many layers, and each layer is about linear and the number of states I want to record. So I'm here, notice I'm recording all my states too. I'm not going to give you the last output. So I can basically understand recursive languages that eventually stop. And even if you want to think about what's the power of this in the context of randomly computable functions. So if you have a randomized Boolean function, so Boolean functions with some random bits, and computation means that you compute true or false with more than probability 1/2, say true, more than probably 1/2. Then there's a deterministic neural network, so the ReLU MLP I just described, which with a relatively similar complexity computes the same function. There's a bit of a penalty over here, which could be improved if one wanted to study it. But anyways, the point is all these results are very much outside the scope of a classical approximation theorem. But like, how do we now relate this back to approximation guarantees? Well, so here's maybe the last thing I want to say about the first project, which is the following, which is what is like a universal approximation guarantee, which is optimal for, say, a low regularity function, so like Lipschitz or sub-Lipschitz. Well, basically what you'd want to do is you uniformly grid up your space to some specific grid size, depending on the regularity. And you attach a little spike at each one of the center points of the grid. And all you want to do is then memorize all the spikes and decide how high they are. The height of the spike is going to be f of the center point of that grid point. Cool. So that's literally an algorithm that does the universal approximation theorem. And here's an implement, like a sketch of it that I did quickly on my computer. And so, for example, suppose, just to give an example, if I have this like funny wavy function and I uniformly sample a relatively fine grid and I plug in the previous algorithm, those little points are exactly what you'd get from a neural network that emulates this algorithm. And who is this algorithm? Just to be clear, this is just a simple realization of what the universal approximation theorem is computing on a finite grid. So the key point is, you notice that the number of grid points scales exponentially in the dimension, because yeah, if you have 1/n precision, you have d axes, you have n to the d parameters if it's Lipschitz, and worse if it's lower regularity. And therefore, in other words, this is a NP hard algorithm, and therefore you get exponentially large networks. And so in other words, the key point I'm making here is not that I can draw this picture, but rather it's just a different way to think about also, as a consequence of our results, you can also think about how a classical approximation theorem fits into the question of how hard is it to compute this guy. Okay, cool. So now I'm gonna like hard transition into the new stuff. So this stuff came up, is on the archive, I think in end of January or beginning of February, wherever the code deadline was. So, right. So one funny thing that happens in this project is you also will, and I'll show you in the first couple of slides, is we showed that there exist neural networks that do these things, like compute these algorithms and so on, or these functions, and we exhibited them. But if you ask yourself, if you were just to randomly come across it by training or by random selection or something like this, would you actually get this configuration? Like, how hard is it to actually compute something? And so this is important because I think it's important. Some people might also. It's important because if you want to use a neural network and you want to claim that the neural network is doing some kind of reasoning, well, can I certify for you that it is? You know, not so obvious, because if the configurations are very unlikely, it's very unlikely that the network is just not doing more than memorizing input-output pairs. And we'll come back to this in different ways. So this is now joint work with a friend of mine, Wen-Hao Lee. So he's doing his PhD at Toronto, Krad, who is at McMaster and also at Vector, and again, Dennis, who is same PhD student also. So Krad is a temporary group member. He's going to move on to bigger and better things in a moment. Okay, so here's just like a toy example. Let's just think about how hard is this certify in some sense learning not, like one of the easiest Boolean functions possible that's not completely trivial. Okay, so again, it takes 0 and gives you 1. It takes 1 and gives you 0. Okay, not so bad. So I'm going to take a neural network with 3 parameters. I'm going to just look at it, well, I'm going to ask myself, what do the parameters have to be? Like, what are the possible solutions to this problem? Okay, so bear with this little exercise. It's like a cool down warm up. I don't know. Okay, so the first thing is if it needs to take 0 to 1. So plug in 0 and just get θ3 ReLU with θ2, right? So because the ReLU function, remember, it's 0 if the input is negative, and I want the output to be 1, which is positive, this automatically implies that θ2 has to be positive. This guy has to be positive. Cool. All right. And then when I notice that θ2 is positive, and remember the ReLU function's identity for any positive number, this guy's going to be 0, right? Then I'll make a glet. When I plug in 0, I get θ3 times θ2 has to be equal to 1. So I get this relation amongst θ3 and 1 over 3 to 3 is 1 over θ2. Fine. And just playing a similar game with x is equal to 1, and just doing a bit of computation, I also get another relation amongst θ2. So θ2 could be no smaller than negative θ1. Okay, so what's my little point? My little point is simply that the biggest space of solutions to that problem with this network is a 2-dimensional surface living in 3-dimensional space that has some weird constraints. And an example of a minimal solution, this is like a 1-dimensional curve in a 3-dimensional space. I can couple them all like this. Either way, if you take like this probabilistic interpretation or this topological interpretation, and these are both unlikely sets. They're either measure 0 for like Lebesgue measure, or Gaussian or something, or they're meager, right? They're low dimensional. So in other words, they're rare. So it'd be very surprising that we land on them by some random training procedure, especially if this is one little module inside a bigger network that's supposed to be doing some very complicated computation like the previous thing. So, okay. And not just to drive the general problem home, this is not about not, this is a general thing, but I'll illustrate it with and. So even with and, we want true to go to true. Automatically, this enforces at least one constraint and reduces the dimension by 1. So automatically, the space of like admissible configurations, parameters that will allow you to compute and is lower dimensional than the total parameter space. Okay, so in general, like almost always, except for the constant functions, configurations are rare. Right? So it's unlikely. I personally think, and we'll show some numerics, it is rather surprising if we were to somehow land on the right configuration. Okay, so now the question is, can we construct a different model, which no matter how you train it, no matter how you choose the parameters, even if you choose them smartly or completely randomly, they'll, with probability 1, in some sense, give you a meaningful computation. So can I give you certified reasoning? I'm going to start with this in the Boolean setting because in some sense, in some ways, it's like easier, So, okay, so I'm going to give you 2 fancy operations. For the first, let's actually go from right to left. So we're not going to do any classical neurons. Like here, a neuron, again, will just be like affine activated and then affine or linear activated affine. Okay. We're not going to do that. Our basic operations are going to be these random Boolean computations. And so what they're going to do, they're going to be random binary Boolean computations. they'll do two things. A neuron has like which is random, so the balloons apparently. It's going to do the following thing. It's going to execute one of all this possible 16 binary Boolean operations. Okay, and I'm using color to indicate likelihood. So green is very likely in this picture, and red is very unlikely. It's randomly selects them, and we're going to be able to train the probability that you choose any of those realizations. Let's sample one of those guys, and it takes a pair of inputs. So it has like a pair of two random edges that are somehow correlated, that are connected to previous nodes, and it just randomly selects the output of the previous nodes. For example, this is 0 or 1, 0, 1, whatever. I'll select two random edges, and I'll two random previous nodes, and take the first one as inputs, okay, A, the second one as input, B, and then apply the random Boolean computation to them. And the things I'll be training, like they'll be able to train or the different, like the optimizable things is the probabilities that I select any one of these activations, and the probabilities that the first edge is the probability of connecting any one of these nodes as the first edge, or randomly selecting the second edge. Okay, and the second, those more technical thing is this. So this happens on pretty much all the computation nodes. In the first node, this first layer of our network is going to have a special, like we call the stochastic bit lifting channels. And what this does is just imagine here you have like B bits, I guess B is 3 bits, and we're just going to first duplicate the bits and negate half of them. So if we have B bits, they get sent to the B bits under negation. And then what the stochastic lifting channel is, we say we have like a certain number of relevant slots, B up arrow. So B up arrow is also 3 in this case. And in those slots, you get to randomly select between any of those, like the B bits or their negations in a similar mechanism, right? So again, here we're going to be playing with the probability of selecting, like for example, who goes into the first slot, who goes into the second slot, and who goes into the third slot. And again, here in these pictures, I'm coloring dark green as likely, orange as medium likely, and red as being unlikely to go to this slot. So for example, here, non-X1 is likely, and for here in the second slot, for example, not B is unlikely. Okay, so how does that look like? So the function is going to look similar, like a feed-forward MLP kind of structure, but very different. So the bit lifting channel is just the thing I described here. You can define it formally in the paper. It takes an input, and it takes a random draw, so an event and some latent probability space, and it generates all these boldface parameters, basically. The input is deterministic. That's the bits in our Boolean cube, and it does a bit lifting. So it just randomly selects the thing I just described here. Then it's going to be passed to the next guy. The next guy is going to, down the way, we're just going to keep doing these operations at each node. So then I pick a pair of previous bits, for example, from these slots. I pick a pair, and I execute a random Boolean function from the possible ones I have. I get to choose, I get to play with the probability of any of these choices. And I keep doing this again and again for a certain depth delta until I return to you the output. That's going to be the computation. It's a random function. Okay. So if you really want to see what it looks like, I just give a snapshot at the neuron. So the gate in the neuron. The gate in the neuron is like this. It's just a random variable that's one hot in 16 dimensions. 16 because that's the total possible binary Boolean bit computations. And the thing we get to train is the probability that you hit any of the basic vectors, okay? And that we parameterize just by softmax of some trainable matrix, okay? Trainable 16-dimensional vector. So notice that there's always a positive probability because this guy maps into the interior of the 16 simplex that I can sample any one of these guys. There's always positive probability of sampling each one of them, but I could imagine, at least at a high level, choosing these weights, these parameters in a specific way that I make it extremely likely to single out any given operation. Right? And the edges also have a similar mechanism where I apply softmax to some specific matrices, and the coupling of the second edge is complicated, so I won't say that now, but there's an expression. So what I get is the following. I don't know why the spacing looks like this. I couldn't fix it. So the first things I get is sort of what I call certifiable Boolean reasoning, which is that for any possible selection of the parameters and the random matrices that we determine, and therefore the random function they determine, f hat, with probability 1, I will sample a meaningful Boolean circuit of the following type. If I had B in inputs, my circuit will have B in inputs, okay? If I had, once I give this list of parameters, essentially I'm describing the depth. The circuit will have the right depth, and the width is going to be also determined by these parameters. So in other words, with probability 1, I get a circuit of the exact structure I would like to get. But I'll never, the point is, key point is I'll never get something that's not representable as a circuit. Cool. Second thing is we get the universal reasoning, which means slightly different thing than classical linear approximation theorem and slightly different than the first part of the talk. Here, there is no approximation error, like the first part of the talk, and different from a classical approximation theorem, but there's a probability of failure. Okay, so for every Boolean function, so in B in bits, and every probability of failure, which can be arbitrarily small, okay, there exists an f hat, who actually doesn't depend, like the size doesn't depend on delta, which is kind of curious, f hat, such that with a 1 minus delta probability, so very high potentially, for every input of the Boolean cube, I exactly compute the right value of f of x. Okay. And notice when I couple that with the first guarantee, I also know that f hat has this breakdown as a meaningful algorithm. Cool. Oops. Okay. Yeah, and the second thing I want to say is, okay, what about the efficiency? You know, can I give you a guarantee that, like this is an existence theorem, and this is like a uniform kind of guarantee, but can I guarantee you that also that this thing is not super hard? You know, so okay, that depends. Or probably only if the ground truth function is somewhat nice. And so an example, but slightly more general in the paper, is if my target function, my Boolean function, is a log b in junta, or O log will give you a similar guarantee. You can see the paper. So what that means is, for example, this function has b in bits, sure, but only log of them are meaningful. So somehow this is a very sparse function, okay? So that's maybe good structure. It's one example of a simple or like widely agreed upon good structure in the Boolean setting, but there's of course others. And I encourage people to think about them. And so what we're saying is that, okay, the following. So similar as before, for every failure probability given such a junta, log b junta, there exists f hat, like in the previous slide, computing f with high probability. So exactly making the same guarantee happen, except now I can tell you something about its complexity that's like a stimulating, I guess, mentally, because before it'd be less impressive, the complexity. The depth of this guy is basically logarithmic in the number of effective bits. Right? The width is linear in the total number of bits, not so bad. And the parameters are just a bit more than linear in the total number of bits. So in other words, this thing is like it's definitely less than quadratically complicated to compute. So in other words, we could compute this, and our reasoning breakdown is our Boolean circuit. If you sample a typical outcome f hat, is going to be small. Cool. So this is a lot of nice theory, but like, what does this mean practically, and how does this compare against any kind of reasonable benchmark model? So the proof of concept. So we have some implementations. I'll run you through what these things mean, at least like some key places. Okay. So just benchmarking against a multi-layer perceptron, so like a ReLU MLP, I think it was ReLU, yeah, with classical, with a similar number of parameters as our model. So apples to apples. No, we're not giving our model billions of more parameters. They're about the same amount. And we're asking ourselves the following thing. We're going to generate a bunch of random sentences of a given maximal length, sentences being like a Boolean formula, yeah. And we're going to just try to we're going to subselect a bunch of inputs in the Boolean cube, and this will give us our training data, right? So random Boolean inputs, evaluate the sentence, true or false. That's the pair. And we do this for a bunch of sentences, all randomly, and we train, every time we do this for a given sentence, we train an MLP in one of our models and ask ourselves, how good have we recovered exact input-output pairs matching? So EM is exact match. Okay, so what we're going to see is that MLP does kind of what we kind of expect. It's almost 100% accurate. Okay, so almost 100% probability with very small variance. We're exactly interpolating, like a basic neural network is exactly interpolating the truth, the Boolean Q value to the truth value. So it's almost memorizing the truth table almost exactly correctly for almost every line. That's really cool. And our model is actually pretty close. Slightly worse, but very close, 97% the chance with a slightly smaller, bigger variance. So, okay, is that unimpressive? I don't know. Let's see. Well, the key thing is, what does that slight loss in power gain? Do we gain any do we gain any kind of guarantees that this guy is doing some reasoning? And do we get any interpretability? Yeah, we actually gain a lot. So for that small, like, I don't know, 0.2% loss, what we get is, so SBC, stochastic Boolean circuit, MLP. What we get is, by construction, every time you sample ours, there's 100% guarantee that every single neuron is doing some Boolean computation. Okay, so okay, I should explain what BNR is. My bad. So BNR, it doesn't matter what it stands for. We invented a name for it. It's a very simple test that's exact. That tests if some function is some Boolean function, right? Okay, and I could just describe you an example of one once, but the idea is that is the following. There's a simple test you can run. It doesn't tell you who the Boolean computation is, but you can quickly just test a node by probing its input-output relations to test if there even exists a Boolean function this guy's computing, right? So it doesn't say that we know if it's and or whatever. In our case, we know exactly what the computation is. The MLP, we could by running this little test, we can test that almost in the first layer, L1 is the first layer, only 10% of the neurons are doing a Boolean computation. We don't even know which ones they are, but even only 10% of them are doing some Boolean operation. So they're definitely not doing reasoning in the sense of this Boolean, binary Boolean language, okay? And if you look at all the nodes, only 20% of the multi-layer perceptron are doing some computation. We don't know who it is. We don't know what Boolean operation it is, but only 20% are doing some Boolean operation. So they're not reasoning. This thing is memorizing, right? Whereas 100% of ours by construction is reasoning. So it has like a meaningful algorithmic breakdown. So what we gain for that 0.2%, and also justified by the theory, which is the key thing, is 100% chance of reasoning and not just interpolation, which is quite a big change. And another quick thing, which I find is curious, and I don't know, we just kind of put this in the appendix, kind of interesting actually. Even if you just don't want to open the network and look at what every node is computing, which you could do, right? By construction, you can just quickly query them all and say, what are you typically returning me? And even if you just wanted to go into it, you can get a high level idea of like what is the actual breakdown of the computations that this network tends to favor over this particular problem. For some reason, this network likes, oh, sorry. Yeah, let's look at sorry, these are the UBC is like the ones we're looking at. So we don't have too many constants, fine. They tend to, this network, for example, tends to like XOR or not A and A. Just to explain who not A is, it's the lift of not A. So AB goes to not A. So it's like a not, and it's a not in projection basically. So projection and not. Okay. So anyways, it doesn't matter. The point is you can quickly read off the operations that this network tends to prefer after training. So even lightning fast interpretability. Okay, so conclusions. So there's a few things you can say. The conclusion of the following is like, okay, in the first part of the talk, and this is like a big part of something I'm interested in right now, is, okay, we proved that neural networks can exactly emulate algorithms. And here in this, the first part of the talk, it was any algorithm that's of a circuit non-looping type, completely constructively, more than constructively actually, yeah. Right? As long as the algorithm is runnable on just like a fine precision computer, which you might actually argue is the most realistic setting, you know. But we're working on the less realistic Rn valued for fun now. Okay, we also proved that time complexity of an algorithm is directly, in a very concrete way, mapped to the space complexities, the number of neurons, or not really neuron parameters of the neural network. Okay, we show that universal reasoning implies universal approximation. And by here, reasoning, I'm taking this to mean like computability in the circuit sense. And because I can easily exhibit a very small circuit implementing a classical minimax optimal approximation theorem. So yeah, so this implication is this way and not the other way, it's easy to see. Okay. Now, the other thing is like the little thought experience you had when transitioning from the second part of the talk. We saw that the reasoning or computation is rare. Like these configurations exist. Yeah, that's really cool. But it's pretty unlikely to actually hit it randomly by training or random selection, especially if we want a specific computation to happen in a specific order. That's even more unlikely. Too many constraints. Very rare. But then you can construct using this mechanism. So we did this project for Boolean reasoning problems, but I could easily imagine doing this for other kinds of languages, right? I don't think there's really any restriction there. But one can construct special neural networks, specialized to the language you care about, here binary Boolean reasoning, that were certifiable reasoners. They always produce like a meaningful circuit breakdown. You can break down the steps if you want, and they're also universal, not they could represent anything. And finally, I think it's a cool thing is it's not all just theory. Even when you put it to practice, like there's a very massive gain in 80% reasoning increase, which I mean like 100% of our neurons are reasoning in some Boolean way, whereas the benchmark is like 20% is pretty bad for a very small loss in performance. Right, so we don't memorize, we can actually have this breakdown. So anyways, there's so much more to talk about and stuff, but I mean, this is where the state of things are as of the archive, but hopefully in the future, there'll be more stuff.
Yeah. All right. Yeah. Thanks a lot. Let's thank our speaker, and then I will stop the recording here so we can all ask our potentially not great questions. of which I have several.
Okay.
So let me see. There we go.